This meeting is being recorded.
In section 5.6, we're now going to look at how symmetry can affect our determination of chirality being present in a compound. So we've learned that when a compound has something called a chiral center, it would be a chiral compound. So this is true for every compound that has one chiral center. So only one, that compound we can say will always be chiral. But when we have more than one chiral center, depending on whether or not there's a plane of symmetry within that compound, it may still be achiral. It may not be a chiral compound because of that symmetry. So let's look at an example down below where we have two different stereoisomers here. So we have the trans 1,2-dimethyl cyclohexane, and then we have the cis 1,2-dimethyl cyclohexane. So both of these have two chiral centers. So we have the trans has those two, and then our cis, we have these two chiral centers. But only one of these will be considered a chiral compound. So let's take a look at how we can determine if symmetry is within the molecule or not. So let's take a look here. If we were to try to draw a plane here, a dividing line between this molecule, there's no way that we could find a plane of symmetry to reflect this upon itself. So the trans isomer would then be chiral. So over here, this would remain a chiral compound, even though it has more than one chiral center. But over here, if we were to draw this dividing line, find this plane of symmetry in the middle of the compound, right, of the cis isomer, we would see that it is superimposable on its mirror image. So that would determine that the cis isomer of a 1,2-dimethyl cyclohexane would not be chiral. So this is achiral because of that plane of symmetry. So there's a term for this when we have a symmetric compound, that plane of symmetry found, and we have these chiral centers. So a molecule that has chiral centers and then a plane of symmetry, therefore makes it achiral, we would call these meso compounds. So another way to test if we have a meso compound is to see if it would be identical to its mirror image. So we could draw the mirror image of the cis isomer, and then we would see that it could be superimposed on its mirror image. So whenever a compound is identical to its mirror image, even if it contains chiral centers, it would be achiral. Right? So the take-home note here is that just because you have two chiral centers or more, the compound may not be chiral. There's one other determination or one other consideration that we should make. If a compound has a plane of symmetry, we saw on the last slide, it would be achiral. But sometimes compounds lack a plane of symmetry and we still find them to be achiral if it has a reflectional symmetry through a point of inversion. So if we put a central point here, a point of inversion in this molecule, we could see that if we were to reflect this compound upon this point of inversion, this would determine that this compound is still achiral. It has two chiral centers, so here and here, but because of that point of inversion, this compound would still be achiral. So this is less likely going to be seen in examples in homework or on test, but you might hear about it. So you should know about that point of inversion, but you may not have to practice it in problems. So this is our summary. So overall, if there is the presence or absence of rotational symmetry, that is irrelevant to our chirality. So whether we, rotate a molecule 180 degrees, etc., this rotational symmetry does not apply to our determination of chirality. But what we do consider is that if a compound has a plane of symmetry within it, then we would say it's achiral. and that would be with 2 or more chiral centers. One chiral center we know equals a chiral compound, but when we have 2 or more, we can have that plane of symmetry. And then we know that down here, usually a compound without a plane of symmetry would be achiral, but we talked about that inversion center briefly, and that's the exception to that. So let's go back and look at these meso compounds one more time. So we know that all of these wedges and dashes shown, these are all chiral centers within our compound. But again, if we were to draw that plane of symmetry, somewhat like that, in the middle of our molecule, we could see that it would be an achiral compound. Same thing applies here. And if we drew a plane of symmetry in the middle here as well. So all of these compounds, these meso compounds, would have less than our formula would predict for the number of stereoisomers. So these, for example, we would have 2 to the n. So if n equaled 2 chiral centers for all of these, we would think that there would be 4 different stereoisomers possible, but generally with these we would see 3 because of that achiral plane of symmetry that's reflected. So that's everything from this section. We'll continue with the next section on Fisher projections in the next video.